Now we can use the Hess principles about path independence to solve these kinds of problems where we want to find the delta H of a reaction, and we've got reactions that can add up to give that reaction if we manipulate them. There's two rules that we're going to use when manipulating reactions in order to get them to add up to this reaction. The first rule is if we flip a reaction, we're going to flip the sign of delta H. I'll write that down there. Flip the sign of delta H. And here's an example of that. If you've got a reaction where we're going from A to B, we know that we can measure the delta H, or the energy change, by doing delta H equals the sigma over the sum of delta H formation of products minus the sum of delta H formation of reactants. So it's always products minus reactants. So you can see here that if we've got a B minus A, that this is a small number minus a big number, we're going to get a negative value. By small, I mean that we've got the energy is going up, so this number is going to be clearly smaller than this number. If we take a small number and we subtract a big number, the value we get will be negative. Now if I flip this reaction and we go from B to A, so the energies of B and A won't change, but since it's always products minus reactants, you can see that this is going to be a big number minus a small number, so we're going to get a positive value. Now the values of delta H are going to be the same, it's just that the signs are going to be reversed. So the moral of the story is that if we flip the reaction, we have to flip the sign of delta H. Alright, let's say we want to also deal with the second rule, which is multiplying the reaction. If we multiply a reaction, we multiply delta H. So let's say we have a gallon of gasoline and we explode it, and then we have 10 gallons of gasoline and we explode that. I think it's clear that the 10 gallons of gasoline will release more energy than the 1 gallon of gasoline, and that the amount of energy is going to be proportionate. So if we multiply a reaction, we're also going to multiply delta H as well. Alright, so these are our two reactions. We're going to have to manipulate those in order to get this reaction. Now a couple of tips. There's a few tips I want to use in doing this process. The first one is that everything in these reactions we want to get so it's on the same side as what we want in our reaction over here. Now what I mean by that is we've got N2 on the reactant side and we've got N2 on the reactant side of this one. That means that I wouldn't want to flip this reaction because it's already has the N2 on the correct side. If I look at this one, I've got NO on the product side, and here I've got NO on the reactant side. That tells me I would need to flip reaction 2 in order to make sure that this gets onto the correct side. So that would be the first thing I should do, is figure out if everything's on the correct side. I want to ignore any compound in these reactions that appears in more than one reaction, and the reason for that is because by considering those, I'm going to have to consider them in more than one reaction at a time, and that's going to make things complicated. So I'm more likely to concentrate on the N2 and the NO and ignore the O2 for now. Hopefully the O2 will take care of itself once the manipulations are complete. The other thing I want to figure out is whether or not I've got the right coefficients, and I can see that I've got half N2 here and I've got 1 N2 over here, and that means I'm going to have to multiply this reaction by 2 in order to make sure I get the same coefficient. Alright, so let's go ahead and do what I need to do here. First of all, checking the reactions and making sure I have everything on the correct side. As we said, N2 is on the right side, O2 we're ignoring because it appears in two reactions, and NO is on the wrong side. So what I'm going to do is I'm going to flip reaction 2. Now when I do that, this is going to become 2NO2. Now I'm going to ignore the states here because there's none of these compounds that are in more than one state. They're all in the gaseous state, so there's not going to be any confusion by removing the states to do the manipulations here. Now when I flip this reaction, the delta H now, will become negative 114.1 kilojoules per mole. Now the other thing I'm going to have to do is I'm going to have to multiply this reaction here. Multiply this reaction here so that I can get the same coefficients. I've got N2, I've got half N2 here, and I've got 1 N2 here. So what I'm going to do is I'm going to multiply the reaction 1 by 2. So when I do that, I'm going to end up with N2 plus 2O2 gives 2NO2. And when I do that, I'm going to have to multiply the delta H by 2 as well. And that's going to become 66.4 kilojoules per mole. Right, now that I've made those changes, I've made sure everything's on the correct side, and I've gotten the right coefficients in front of everything. You'll see that I can now go ahead and add these reactions together, and hopefully I'll end up with the reaction I need. So I'll go ahead and do that. Now I can see my N2 will come down here, and you'll see that the two NO2s will cancel out. That's a good thing because we don't see any NO2 anywhere in this reaction, so it's gone now. Now down here I've got 2 oxygens, and up here I've got 1 oxygen. I can just treat this like I would any other algebraic equation, and I can say, well, if I'm going to end up with 2 oxygens down here and 1 oxygen down here, what I can do is I can take away this oxygen and just make 1 oxygen down here. So I know that now that's going to be O2, which is what we wanted. We want 1 O2 in our final product, and here we've got 2 NO. Now what I can do is I can take these delta H values and I can add these together, and I'm going to get negative 47.7 kilojoules per mole. The rules I'm using for significant figures are going to be the addition subtraction ones, so we're looking at decimal places. This says 1 decimal place, this says 1 decimal place, so the answer has 1 decimal place as well. Alright, so that's how we would do that kind of example of a Hess law problem.